Hello, welcome to Noise Control and its Management. Today is the last day of this course, and what we plan to do today is close the discussion on single expansion chambers today and also wrap up the overall course. So, yesterday we had introduced this problem where the statement was that we have to design a single chamber expansion muffler, and specifically we are expected to determine the cross sectional area of the chamber, which is S2, and its length, and such that we have a minimum transmission loss of 6 decibels. It can be more, but minimum transmission loss of 6 decibels between 177 hertz and 354 hertz. And in this process we have to make sure that the length of the chamber is as small as possible. So, how do we go around doing that? And of course, we are given the diameter of inlet port, and we are also told that inlet and exit ports are having the same cross sectional area. So, how do we do this problem? Now, to do this we have to get some physical understanding of how this muffler is working. Now, in the last class I had shown that if I plot on the x axis KL and if I plot on the y axis let us say 1 over AT, okay, then so KL, the unit of KL is in radians. When the thing is 0 radians, then 1 over AT is 1, and then so this is the curve for 1 over AT, and this is a maximum when KL equals pi by 2 radians, and then it again becomes maximum when KL equals 3 pi by 2 radians and 5 pi by 2 radians and 7 pi by 2 radians and so on and so forth. So, and KL becomes minimum when 1 over AT becomes minimum when KL is 0 or pi radians or 2 pi radians or 3 pi radians and so on and so forth. So, this is something important to understand. So, what that means is, and this is something we have discussed earlier also, that 1 over AT is maximum when KL equals n minus 1 by 2 pi by 2 radians. Okay. Now, this K is what? It is 2 pi over lambda. So, this is associated with a frequency. So, we want a maximum frequency, at some frequency transmission loss will be maximum, and as we move away from that frequency transmission loss will start declining. So, at some frequency transmission loss is going to be maximum, and as I move away from that frequency transmission loss starts decreasing. Now, we are told that this muffler has to operate from 177 hertz to 354 hertz. So, what I can interpret this data in a way that my parameter 1 over AT should be maximum at the middle of this operating band. So, I will say that F naught should be equal to 177 plus 354 divided by 2, and that is equal to 265.5 hertz. Okay. So, that should be equal to 265.5 hertz. So, what I have written here is that 1 over AT is max when KL equals n minus half times pi over 2. So, there is a small error here, actually it should be just pi. So, that is there, and if that is the case,
then we can say that n equals half plus 2L by C times F naught. Okay. So, how did we get this relation? We get this relation from basically this particular equation, and the only thing we are doing here is that we are substituting k in we have so k is 2 pi over lambda, and I am expressing lambda in terms of frequency f naught and c. So, if I make these substitutions, I get this relation, and let us call this equation 1.
And as I move away, so this pi by 2 corresponds to, so pi by 2 or 2n minus 1 pi by 2 or pi by 2 or 3 pi by 2 or 5 pi by 2, this should correspond to 265.5 hertz. And as I move away, maybe here this should correspond to, this point could correspond to 177 and this point could correspond to 354 hertz, and the peak point should correspond to the midpoint, which is 265.5 hertz. And now let us look at this chart again. So, this distance, so the distance from here to 0 hertz is pi by 2 radians. Then so in that, so the distance between 265 hertz and 177 hertz will be, this will correspond to what, pi by 8, and this is also going to correspond to pi by 8. Okay. So, what I can say is that K2L minus K1L is equal to pi, I am sorry, it should not be pi by 8, it should be pi by 4, because the overall distance is pi by 2. So, this is equal to pi by 2 radians, where K1 is equal to 2 pi over F1 and K2 equals 2 pi over F2, where F1 equals 177 and F2 equals 354 hertz. Okay. So, if I plug in, I can write okay. Oh, so this is 2 pi F, and of course there is a C also there. No, I think I messed it up. So, this will be K1 is equal to 2 pi C divided by, I am sorry, so 2 pi F1 divided by C F2, and 2 pi F1 divided by C and 2 pi F2 divided by C. So, I plug in these things, what I get is 2 pi F2 minus F1 divided by C times L equals pi by 2, and this pi cancels out. So, what I get is 2L over C equals 2L over C equals 1 over 2 times F2 minus F1. So, this is my second equation, and what I do is I connect these two equations, I put in the value of 2L over C in this. So, what do I get? Because I have to compute n. So, n equals half plus F naught divided by 2 into F2 minus F1, and I know that F naught is the mid frequency, which is 265.5 hertz, F1 equals 177 and F2 equals 354. Okay. So, n equals 1.25 based on these values, but I know that n should be an integer number. So, what are the numbers, integer numbers which are closest to it? So, I have two possibilities, n equals 1 and n equals 2. So, I have to now check both these solutions and see both these possibilities and see which n will be a good choice for us. So, first we try n is equal to 2. So, if n is equal to 2, then L should be what? It should be, we look at this expression, n is equal to half plus 2L plus 2L by C times F naught. Okay. So, n equals half plus 2L by C times F naught and try n. So, if n is equal to 2, then what we get is 2 equals half plus 2L. So, 2L by C, and what is C? C is 3, this is the velocity of sound, 337.5, and what is F naught? F naught is 265 hertz, 265.5 hertz. So, what I get is L, if you do the math, comes out to be 0.953 meters. Now, for this L, we should have maximum value of transmission loss, which means that KL should be either pi by 2 or 2 n pi, 3 pi by 2 and so on and so forth. So, let us calculate sin KL for this L. So, sin of KL, so what is K? K is 2 pi by lambda, which is 337.5 and divided by 177. So, this and that into 0.953 and that comes out to be 0. So, obviously, this is not okay. This is not okay. So, we are not happy with this solution. So, the next thing we do is we try n is equal to 1, because if this term is 0 for 177 hertz, essentially what it will mean is that 1 over 80 at 177 hertz will be 1, which means transmission loss will be 0. So, that does not meet our requirement of minimum 6 decibel attenuation. So, now we try n is equal to 1. So, in this case L is equal to 1 minus half into 337.3 divided by 2 into 265.5, and that comes out to be 0.318 meters, and we find that K1L equals 2 pi into 177 by 337.3 into 0.318, and this works out to be pi by 3 radians or 60 degrees. So, sine of K1L is equal to root 3 over 2 in our case. So, the good thing is that it is not 0, and maybe a solution can be worked out for this value of n. So, with that understanding, we now compute transmission loss. So, at 177 hertz, we need to have a minimum transmission loss of 6 decibels. So, the rule is, so the relation is transmission loss equals 6 dB and that equals 10 log of 10 of 1 over AT. So, this gives us AT to be 3.981. So, now I know AT, oh I am sorry, this is not AT, it is 1 over AT. So, for this value of AT, I now compute the aspect ratio, which is the value m. So, I know that 1 over AT equals, we had the expression 1 plus 1 by 4 into m minus 1 by m whole square sin square k 1 L. So, now in this relation we know this, we also know this term, but we do not know this. So, we will compute m. So, we will write this expression. So, 1 over 80 is 3.981 and this equals 1 plus 1 by 4 into m minus 1 by m whole square, and sin square k L is 3 by 2 or 3 by 4. So, this gives us a quadratic equation, and the quadratic equation is m square minus 3.987 m minus 1 equals 0, and this gives us two solutions. So, one solution is m equals 1.9937 plus 2.236 and the other solution is 1.9937 minus 2.236. So, we do not like the second solution because it gives us a negative value of m, which is not realistic. So, we choose the first solution, and what that gives us is that m equals 4.224. So, now that we have calculated m, we now calculate the diameter of chamber, and the diameter of chamber is equal to 250 divided by 4.224. So, where is this 250 coming out from? It is coming out from this parameter which we had defined. So, d1 is small d, this is 0.25, we are interested in this d. So, whatever is the ratio of capital D and small d, and if you square it, that will be same ratio as m. So, that is how we are getting this expression. So, d of chamber is 250 divided by 4.224, the whole thing under square root, and this gives us as 514 millimeters. Okay. 514 millimeters, and for this value of d, my AT max, and this will happen at the midpoint frequency. So, what is the value maximum transmission coefficient? This will be equal to 1 plus 1 by 4 m minus 1 by m whole square, and that is equal to 4.975. So, transmission loss equals 10 log 10 of 4.975, and that equals 7 dB. So, this is how we compute our muffler, okay, the dimensions of the muffler. So, what we have done till so far is we have explained you how to design a single chamber expansion muffler, and the area of mufflers is a very wide field. So, this just gives you entry into this vast area, but I hope what we have accomplished through this discussion on mufflers is that you have become familiar with different approaches of designing mufflers, and with this as a basic material, I hope you will be able to take this understanding and knowledge further and adapt it and learn more, so that you can meet your needs in case you think that a muffler may be a good idea to control the noise problem which you may be handling. So, that brings us to the conclusion of this course. Over this 12-week period, we have discussed a large number of topics, and what we have discussed is we started with the basics of acoustics. So, we introduced a large number of terminologies, decibels, bands, frequency bands, octaves, decades, transmission loss, and so on and so forth. And then we developed the one dimensional transmission wave equation for Cartesian system as well as spherical system. And then we developed our transmission line equations. We tried to understand the meaning of impedance, and we ran several cases, and then we walked into the area of noise estimation. So, we learned how to estimate noise both indoors as well as outdoors, with or without reflecting surfaces in the near field or the far field, and we did this for several types of machines. For instance, if you have a fan or a blower or a motor or a compressor and so on and so forth. And in the concluding portion of this course, we learned several technologies which can be used to reduce the noise levels inside the room or outside the room, and we learned this through usage of several techniques and tools like partitions, barriers, resonators, side branch mufflers, expansion chamber mufflers, and so on and so forth. So, I hope this has been a useful course for you. Of course, the area of noise control is very vast, and what I think I have tried to do is to give you a comprehensive picture of some of the important points and background material, so that it gives you a more easy entry into the area of noise control. And if you have any questions, please feel free to approach us, and in case you have some specific doubts, you also have the choice to look at some of my earlier NPTEL lectures in the area of acoustics. So, that may be useful, or you can look at some of the reference materials available on the internet which I have shared with you, or you can approach us through your questions, and some of the TAs or me will be more than happy to help you with those questions. So, thank you very much, and my best wishes for the future. Thank you. Bye.